Hello, everybody. Looks like everybody's coming in now. I got in right at 5:30. Actually, it's now 5:31, so I just barely got in on time. Anyways, sorry about the delay. It took me a little longer to get in, even though I'd started up at about 5 till. So let's begin with asking, does anyone have any questions? I just made your test 4 available, and I'm working on your test 5. Uh, it should be available really soon. But when I copied it in, it's missing a couple questions. So I've got to wait till that loads in and put in the appropriate question. It has completed loading in. Let's see if it's got the question now. That will be July 24th. Let's edit that. I'm working on it right now, everybody. So bear with me a second while I wait for other people to come in. As I said, anybody have any questions, you can ask them now. 24th, 24th. You'll also notice if you actually look, oh crap, everything's missing. So let's hold off on test 5. I'll do this after class. I don't unpublish it. There you go. Okay, so test 5, I was published for a second, but I just unpublished it. I got to fix it. It's like 4 questions are missing out of it. So I've got to redo that. But test 4 is up and ready, and that's the one that's due on Monday. I ended up changing my idea or my plan of what I was going to do. It was supposed to be like one was going to be due this Sunday, which for you guys means this Monday, and then the next one was going to be due like Wednesday, which for you guys would mean, or excuse me, it was supposed to be due like Tuesday, but for you guys that means Wednesday. So I realized also that the next face-to-face test is Wednesday and Thursday. So that means you guys have a face-to-face test on Wednesday already. So what I did is I just went ahead and pushed that second due date back to the following Sunday, or actually for you guys for the following Monday. So it's the 24th. So you got one due on the 17th and one due on the 24th. And I decided to make them both just just online. So you don't have to do Respondus lockdown browser. It's open notes, open books, open Google searches. Again, the main rule I'm trying to shoot for here, including the next rule that you hear, is you're not supposed to communicate with anybody that's actually seen any version of the test. So in doing so, I say that means you're not supposed to check out any websites or pages or anything that were created after today or later, because someone could, in principle, go take the test right now, quickly make up a web page, and if I hadn't put that rule in there, this would be completely fair, and they just put up the questions. Okay. So hopefully nobody's doing that anyways, because the problem is we have a very limited number of physics problems we can solve. I mean, there's sort of an infinity of them, but to be honest with you, there's an infinity of all the different wordings and things we can do. But the crux of the problem, i.e., what equations you're using, what things you're going to solve for what, and ones that you can actually solve without having to write code. That's a limited number of problems. So it's ideal if you guys don't share this information that you see on any test or anything like that with anybody. I don't mind you sharing it with each other in class to help each other in your studies, but ideally just don't share it with the next generation of students or even just next semester's students. So that's what I'm shooting for. Hi, Ron, how you doing? So no one has any questions for me? All right, well, you'll see test 4, the one that's due on Monday, is on chapters 21 and 22. So that's really the Gauss's law, the Coulomb's law and Gauss's law, which we finished out last time, actually time before last, where I actually had, maybe it was 2 or 3 times ago, because we had a couple of days we missed in there. But that was the one where I was using Gauss's law to exploit the symmetries and our understanding of Coulomb's law to solve Gauss's law for the electric field magnitude that happens to be sandwiched in that little integral equation. So that's the technique that you have to learn for chapter 22. And then, of course, last time what I did was I finished all three types of symmetry and using this new, what I call a paradigm of how to solve Gauss's law, actually how to derive capacitance using a three-step process. And that's supposed to be a paradigm that's sort of a litmus test for completing this course. You should really be able to do that. You should also be able to do the similar paradigm for starting with either the law of Biot-Savart and Ampere's law, which are the equations that allow you, in some sense, to derive the magnetic field. And then once you have the magnetic field, you use that and the definition of magnetic flux, which is the integral of B dot dA. And when you use the integral of B dot dA, that gets you the flux, and turns out that the definition of self-inductance is the magnetic flux divided by the current. So that's another three-step process you can go through to derive the self-inductance for a inductor. And the typical inductor that you're probably used to is just a solenoid. And then there's, of course, a solenoid where you take and bend the solenoid back into like a donut, and then it's called a toroid. Those are the two major ones, but there's other types as well. Just about in some sense, almost every circuit element has a little bit of capacitance and a little bit of inductance that you could assign it. And I'm keeping it vague like that because I don't really personally understand it that well either. But I do know that in some sense, all circuit components have some inductance type character as well as some capacitance type character. And I know that from reading the histories and reading the writings of Maxwell and Faraday and Oliver Heaviside. And those people are brilliant, and I'm just a teacher. So I understand my science pretty well. I am not a researcher, and therefore I don't necessarily understand all of the little nuances. But when Oliver Heaviside says something, I'm pretty confident he's almost certainly going to be right. So that's the impression I got specifically from him and Faraday, and well, maybe to a lesser extent Maxwell, but still somewhat to Maxwell. So hopefully everybody saw that. I've already posted the video, of course, and tonight we'll post this video, but I've got to work now with some more capacitor problems. So last time I gave you some formulas to use, like the energy stored in the capacitance is 1/2 CV squared. Of course, if you don't know capacitance and voltage, you can use C equals Q over V to eliminate C, for instance, and then it'd just be 1/2 Q, that'd be Q over V. So that'd be 1/2 QV. And then also, if you let's say don't know Q and V, maybe you want to eliminate the V. Well, V is Q over C, so you can replace that, and you only get 1/2 Q squared over C. So those are the three versions of the energy stored in a capacitor. I'm going to take a special case, not unlike what we did with Gauss's law. Remember when I calculated the electric flux for a spherical charge distribution, or you could also say for a point charge at the origin, but I actually pretended it was a spherically distributed charge distribution at the origin. Knowing the symmetry of exactly how Coulomb's law works, I was able to calculate the flux by choosing a really good Gaussian surface, and got an answer that the electric flux was the charge Q over epsilon naught. And even though I derived that for a very specific case of a spherical charge, that turns out to be the exact right answer for Gauss's law. What is the electric flux? Well, that's Q enclosed over epsilon naught. So similar, we're going to take the energy, U equals 1/2 CV squared, and I'm going to plug that in or plug in the values of C and V for a capacitor and derive a energy stored equation. And what I'm ultimately going to get is an energy stored with a little factor in it that looks a lot like the volume of the capacitor. And because of that, I can pull that to the left-hand side, and it'll become, instead of energy, it'll be energy per unit volume. And that gives us an expression that's related to the electric field that happens to be, even though we derived it for a capacitor, happens to be the exact right answer again. And I'll make parallels to that with regards to the magnetic field. So that's what we're working on today. So does anybody offer again, does anybody have any questions about any past homeworks or anything like that? The tests as well. As I said, we have a test on you guys, you have labs on Mondays and Wednesdays, so your test will be in with Mr. Mitchell on the 19th as well. So we're going to have a face-to-face test. In that case, it should be on it'll probably be on 23 and 24, but it might be on 24 and 25 or 23, 24, and 25. I'll let you know that probably Monday of next week because I'm going to make it this weekend. All right. All right. Well, I've got some ideas and some things that I want to work with you guys. So I'm going to go ahead and do that. And I'm going to start off by doing hopefully something that you've already done, at least in the more complicated in the less complicated case. Hopefully you've already looked over how to use the capacitance formula for the equivalent capacitance in series, the capacitance formula for the equivalent capacitance in parallel. And you've probably looked at some examples in the chapter. I'm hoping that's what you've done because really the way I teach this is I'm trying to show you sort of the nastiest of the nasty. And then some of them I actually show you in most chapters. I show you the easy ones too in the chapter. But in this case, since we had to take a day off, I was giving you all the formulas in hopes that you would actually look at the chapter ahead of time. So it may be a little daunting, this first case that we're getting ready to do. So I just want to warn you, it's a long process, but it's also a valuable process because I'm going to teach you how current acts when you connect a battery to a bank of capacitors. Okay, so that's what we're going to do here. I am going to share my screen, and I'm going to share my screen with the appropriate app because that would come in super handy. Yes, there it is. Okay, so let's do that. I'm going to say share screen. Do that. And hopefully this will come on lickety split. Cool. A little faster than normal. That's making me feel pretty confident already. Okay, so my confidence is completely gone now. It's obviously gone to poop. Oh, finally, yay, it's here. Okay, so I pulled up the chat window too in case anybody tries to chat anything. Hopefully I'll catch it. And now you guys are looking at a bank of capacitors with one battery. So notice this is a 12-volt battery. This is very common practice, by the way, by drawing the symbol for the actual element of the circuit. There's no need for me to actually put the unit on it. But there is a need, of course, for me to put the prefix of the unit on it because it's obviously important to know whether these are microfarads or nanofarads or picofarads or actual farads. So in this case, I've got 6 capacitors. And in fact, notice they go 1, 2, 3, 4, 5, 6. So the 1 microfarad capacitor would be one I would call C1, and the 2 would be C2, and the 3 would be C3. The 4 and the 5 would be C4 and C5, and the 6 microfarad capacitor would be the C6. So if I inadvertently use that terminology, you'll know what it is. Okay. Now you'll also see that there is something that looks like a capacitor because capacitors are drawn as 2 parallel lines, but of equal width. There's 2 parallel lines, but of unequal length. And in that case, that means it's a battery. And in fact, the long side is the positive side. So it wouldn't hurt if I took the time to write plus right here and a minus right here. That's going to come in handy because I'm going to do some stuff where I'm going to imagine like I'm a bot of some sort where I can look at, or actually I should say a robot, so y'all don't mistake me with a chat GPT type bot or something, but I mean a robot, where I can just look at something and up my heads up display will pop up and tell me what the voltage is. And what I mean by that is I'm going to draw these little bubbles, and there'll be like a little line coming from a point on the circuit, and then there'll be a circle, which is a bubble, and in that bubble we'll have like 0 volts or 12 volts or something like that. And that's basically me taking a multimeter like you guys have worked with and placing the black COM port connecting it to ground, either ground in the circuit or say the little mouth looking thing on a receptacle of a house or a building or a classroom. And then the red probe, which is connected to the V omega side, that would be exactly where the little bubble is popping off. So that's something I'm going to use as well. So what I want to explain to you is what exactly happens, and I'll give you a sort of model of what is happening that can't be reality, but in some sense, it doesn't matter if it's reality or not. It behaves as if it is reality. So that's important to understand. So what I'm going to tell you is we have a 12-volt battery. The 12-volt battery is connected to a 1 microfarad capacitor, and then that wire goes from the 1 microfarad capacitor, splits off to make a parallel bank. But here's the weird part. It goes down and there's a single 3 microfarad capacitor on the bottom leg, but the top leg goes into a single 2 microfarad capacitor and then breaks up into a parallel leg of 4 microfarads and 5 microfarads. Okay. Then that regroups to a single wire and runs back into the wire from the 3 microfarad capacitor, at which time there's a single wire, runs to a 6 microfarad capacitor, and then goes into the negative side of the battery. Okay. So what's going to happen here is this battery seems, and this is the part where I said it's like a model of what's happening, but it's not really what's happening, because obviously a battery doesn't know stuff. It's not it's not, well, I don't want to over anthropomorphize it. So it doesn't know all the stuff. It just happens to behave this way. So it has, in some sense, the ability to tell what the net capacitance of this entire circuit is. And it only spits out current, or excuse me, only spits out charge in an amount that's reasonable for that equivalent capacitance. So in other words, this power source, this battery, doesn't really know anything different than as if there's just one big capacitor. And I say big, and I don't mean necessarily big in capacitance, but there's just one capacitor in the circuit as far as the battery is concerned. And that capacitor is the equivalent capacitance of all those capacitors, okay, which is not necessarily easy to calculate. But either way, that's the way the battery behaves, and therefore it sends out using C equals Q over V, so that Q is equal to CV, where C is the equivalent capacitance and V is the 12 volts. It sends out a Q of that quantity, and that Q is going to appear right here on the 1 farad capacitor. Okay, because this is directly in series with it. So all of the charges have nowhere to go but to that first face. Now, since it's on that first face, and you know that capacitors are made and wires are made of conductors, we know that what's going to happen is all that charge that the battery sent out is going to build up on that bottom face of the 1 microfarad capacitor. And then we know from what we studied about inductance and polarization and that sort of stuff in chapter 21, we know that that's going to compel all the positive charges in the top plate of the 1 microfarad capacitor. All of those guys are going to run away, leaving the top plate with an exactly equivalent negative charge. So if for instance, the charge that would be sent out was 8 microcoulombs, then what we're going to say is the total charge sent out of the battery is 8 microcoulombs. 8 microcoulombs is going to be established on the bottom side of that 1 microfarad capacitance, and then negative 8 microcoulombs is going to establish itself on the top plate of the 1 microfarad capacitor. And then that positive amount of charge that's running from that negative plate now is running up, and it's going to go to that junction that breaks off into the parallel part. Some fraction of the 8 microcoulombs is going to go to the top leg, and some other fraction is going to go to the bottom leg. And the fraction is decided by the fact that C equals Q over V. And for any two items in parallel, they have to have the same V. So if they don't have the same C, that means they're going to have a different amount of charge. But those charges, the charge that goes to the top leg plus the charge that goes to the bottom leg, have to add to give you the 8 microcoulombs if that really is the charge that it's going to send out. Does that make sense? Anybody have any questions about that? So some fraction of that 8 microcoulombs is going to go to the top leg, and that whole fraction is going to appear on the 2 microcoulomb left-hand plate. And then that's going to induce an equal but oppositely charged right-hand plate. And then the positive that's running away from that right-hand negative plate is going to choose part of it to go to the 4 microfarad capacitor and what's left to go to the 5 microfarad capacitor, again, in such a way that the 2 voltages are the same, but since the capacitances aren't, the charges can't be. Okay. Now, that's going to compel the left plate on the 4 microfarad capacitance to become whatever charge it got. And then the negative is going to be the same charge, but negative. And then at the bottom, the remaining of the charge that the 2 sent to it will go to the 5 microfarad capacitor. That left plate will become positive. That right plate will become equal but negative. And then all that charge will come back together and go to the little junction where it meets back up with the wire that went through the 3 microfarad capacitor. The 3 microfarad capacitor is going to take its part of the charge and establish the positive amount of that charge on the left plate, and then the negative amount on the right plate. And then that positive charge is going to run from it and combine with the positive charge that's running from the little negative bank. And that's going to leave and go to the 6 microfarad capacitor. Now, it doesn't have any other choice. So if in fact the battery sent out 8 microcoulombs, all 8 microcoulombs is going to come to the 6 ohm capacitor as well, or the 6 microfarad capacitor as well. So both the 1 microfarad capacitor and the 6 microfarad capacitor are going to have the exact same amount of charge. And I'm telling you that, but I'll also show it to you, because the way this works out is it constantly gives us ways to check for internal consistency. And the ways to check for internal consistency, for instance, is the sum of the voltage increases and decreases across any leg has to add up to give you the total voltage difference. So for instance, let me stop for a second and use one of my bubbles. So here's one of my bubbles. You're allowed to, just like in potential energy and conservation of energy and 241, you're allowed to call the 0 of potential energy anywhere you want. So you could take, the ground level and call that U equals 0, or you just might take the lowest level on the roller coaster and call that U equals 0. It doesn't matter, right? So the same thing happens with voltage. You can call the ground anywhere you want, because that's really just electric potential. So I'm going to assume that the negative side of the battery has a voltage of 0 volts. Now, I want you to understand that that is an actual voltmeter reading. And again, the COM, the black part of your multimeter, would have been stuck to ground, which could be that spot right there. And then the red part is stuck where the bubble's stuck. So in that case, they'd both be at the same spot. That's why it's reading 0. Or alternatively, you could have stuck the black COM port probe directly in that little mouth hole in the light receptacle, the one that saw the little round, half round, and then square thing. That's the ground of a light receptacle. So you could put the black in there and then put the red right to the left, right to the right of that negative terminal of the battery, and that would be cool too. Now, the other thing that we can do is we can draw a bubble right here, and this bubble is going to be 12 volts. Again, I might run out of space and just write 12 or 0. Just know that those are all volts. Okay. So that's what we have here. And in fact, if a current is running, and current, by the way, is only going to run, current is the motion of charges through the wire. So the number of coulombs of charge that flow every second is the definition of what an ampere is. And while the charge is leaving the battery and accumulating on that bottom plate of the 1 microfarad capacitor, there is a current going through the circuit. But that current, of course, is going to stop as soon as it reaches that whatever charge it has to have, which is the total charge that the battery is going to send out. But the key point is wires and everything has, except for maybe superconductors, essentially everything has some resistance. So from what we know of Ohm's law, V, the voltage drop is always equal to I times the resistance. So the voltage will technically drop from that 12-volt spot to getting up to that 1 ohm bottom plate, or excuse me, 1 microfarad bottom plate. But the drop is going to be so small, it might literally be like 1 1/3 decimal place. So I'm going to tell you that this spot right here has a voltage also of 12.0 volts. Okay. And like I said, that's probably right to the accuracy that I'm putting. So if I had 2 decimal places, I might actually see that it's 11.95 or something, right? Now, I do know that because there will be a charge on this capacitance and C equals Q over V, I then have a Q and I then have a C, and that gives me a voltage difference. And of course, the positive side of a capacitor has a higher voltage than the negative side. That's part of what we were doing when we were calculating the voltage difference from one plate to another, is I consistently left the negative plate going to the positive plate so that the voltage would come out positive. So whatever the voltage is, which you can calculate by taking the charge that hits the 1 microfarad capacitor and dividing that by the 1 microfarad, that will give you the actual voltage. Well, that voltage will be how much lower the voltage of the top plate is compared to the bottom plate. And okay, of course, the top plate's at 12. So if the voltage drop was 2 volts, then it would be 10 volts at the top plate. Does that make sense to everyone? Anybody have any questions on that? So that's part of how we're going to deal with this. So the first thing I'm going to do is I'm going to find C equivalent. So this problem is asking me to find C equivalent and I'm going to say Q. That's the total Q that the battery sends out. That's why I didn't put any subscript on it. Q1 V1, and that's the voltage across capacitor 1. Now remember, when I say capacitor 1, I numbered them 1, 2, 3 by using the actual microfarads as 1, 2, 3, 4, 5, 6, right? So you should know what I'm talking about there. So that's V1. I also want to know Q2, and I want to know V2, and I want to know Q3, and I want to know V3. I also want to know Q4 and V4 and Q5 and V5 and finally Q6 and V6. Okay, so that's what I'm actually trying to figure out here. I'll separate this from the rest of this by just putting that like that. And hold on a second. My students, hey, Shawnee, Austin tried to call me. I'm sure she's just asking about the apartment, but if you give her a call, let her know I'm in class, that'd be great. Thanks, hon. All right, that was my Shawnee Bear, my wife. So just had to get her because my daughter's calling and all that good stuff. All right, so now we got that, and you have some idea what we're doing. So I'm going to try to work out and show you using our formulas. Remember, the formulas we're going to use are the following. I'm going to say solution, and I'm going to mention that 1 over C equivalent in series is 1 over C1 plus 1 over C2 plus dot, dot, dot. That's one formula we're going to use. And the other formula we're going to use is C equivalent in parallel is equal to C1 plus C2 plus dot, dot, dot. So that's really where we're going with that. And I'll also try to keep this diagram separate. Now, I went ahead and drew this well before class because it takes a while to draw such a diagram. But if you look, I actually did it for 3 pages in a row just in case it takes that much work. Okay. So first off, I'm going to try to find the simplest place. I usually tell students to go to the innermost pair of capacitors, and I found myself trying to define exactly what that was to students, and I found it kind of difficult. So I think I'm going to change the wording. I'm going to say I try to find the simplest set of capacitors that I could replace with an equivalent capacitance. Okay. So for instance, the 2 and the 3, I can't do because the 2 is actually not in parallel with the 3. It's in series with a pair of capacitors. And those 2 configurations are then in parallel with the 3. So I can't do that one. So really all I can do at this point really is the 4 and the 5. And those 2 are in parallel, or excuse me, those 2 are in parallel. So I can replace that with what I'll call C equivalent 1. So I'll say C4 and C5 imply C equivalent 1 is equal to 9.00 microfarads. Okay. So that's because those 2 are in parallel, and in parallel capacitors just add. In other words, the capacitance of the 2 parallel capacitances add to give you the total capacitance of the equivalent capacitance. So now what I have is a .00 microfarad capacitor in series with a 9.00 microfarad capacitor. And I'm just drawing that little part of the wire, right? But now I have 2 capacitors that are in series, and therefore I can actually simplify them. So that's the next simplest state. So I'm going to say C2, which is a 2 microfarad capacitor, and C equivalent 1. For that one, I see that these 2 guys are in parallel, or excuse me, are in series. So their reciprocals add to give me the reciprocal of the right answer of the equivalent one, which I'm going to say is C equivalent 2. So I'll say 1 over C equivalent 2 is equal to 1 over 2 plus 1 over 9. So let me take a second and say, notice I'm not writing the 0.00s. I'm not writing the micros. In fact, that's this type of calculation lends itself quite easily to ignoring the SI prefixes, and you'll just know that whatever you get is going to come out with the same SI prefix. So the least common denominator between 2 and 9, clearly 2 doesn't go into 9, so we have to start doing multiples of 9. Obviously, the smallest multiple of 9 that 2 goes into is 2. So that's going to be 18. So basically, I have 9/18 plus 2/18, right? And that gives me, of course, 9 plus 2 is 11. So that it gives me 11/18. Now, 11/18 means that C equivalent 2 is 18 over 11, which I think you all recognize is 1, and 7/11, which by the way happens to be my wedding anniversary. And I don't know, y'all probably didn't know it, so you didn't take advantage of the fact that the good people at Southland Corporation was giving everybody Slurpees for 11 cents on that day, and it was all because of mine and my wife's anniversary. So just so y'all know. Now I happen to know off the top of my head that 1/11 is 0.090909. So guess what? 7/11 is 636363. So this is actually equal to 1.6363 microfarads. Okay. So that's just the nerdy stuff you learn when you're a nerd that likes to pay attention to arithmetic and tries to make up for, how bad they did in school in the past. So now I have basically I'll draw it this way. Again, I'm gonna do a double arrow whenever I try to re-represent what circuit I have. Now, what I've done is I've reduced the 2, the 4, and the 5 to one capacitance. So now what I have is a wire coming out going into a 1.6363 microfarad capacitor that happens to be in parallel with a 3.00 microfarad capacitor like this. So that's what I have now for just that part. I think y'all can tell what part I'm drawing there, right? Now that's the next simplest part. In fact, that's 2 parallel capacitances. And parallel capacitances, the total capacitance or the equivalent capacitance is just the sum of the capacitance. So this means that C equivalent to, and notice I'm trying to make a point to write a plus symbol there that's not to be confused with addition. I'm making sure you see the little line connecting the bottom of the vertical with the left-hand side of the horizontal. So this is C equivalent to and C3. In this case, they're actually parallel. So I just have to add them and I get 4.6363 again, with the second 6 and 3 being non-significant digits. That I'll call C equivalent 3. Okay. In other words, the third equivalence capacitance I did. Now, what that means is I have a net capacitance of the entire thing is basically, I can draw the whole circuit again. I can say, here's my 12-volt battery. And then over here, I have a 1.00 microfarad capacitor in series with a 4.6363 microfarad capacitor, which is in series with a 6.00 microfarad capacitor. And that comes back to the original power source, the battery. Does that make sense to everyone? So often I would draw this drawing and then say equals and draw another drawing with just the part that I changed, and then draw another equals and another. So I'm trying to do the equivalent because I know that's pretty helpful to students to see it. Hopefully this way is helpful too, because it's a little bit harder to do otherwise. Okay, so now I've got the equivalent of the whole circuit. So this is actually going to be the whole equivalent capacitance of all the capacitors. So what I'm going to do is I'm going to say that this gives me 1 over C equivalent, which is what the problem asked for, is 1 over 1 plus 1 over 6 plus 1 over. Now, here's a case where I've got 4.6363. I don't really like 4.6363. In fact, I'm going to say that 4.6363 is actually 4 7/11, which happens to be 4 times 11 is 44, plus 7 is 51/11. And I think that's right. Let me double check my arithmetic because I can make some really awesome arithmetic mistakes. Yeah, that's it. 51 over 11. So the reciprocal of 51 over 11 is 11 over 51. Okay. So I like working with numbers and ideally not using calculators at all. So I'm not going to waste much time trying to find the least common denominator for these beasts. I'm just going to assume that 6 times 51 will do. Okay. So 6 times 51, 6 times 50 is, of course, what, 300? And this would be 306. So the common denominator that I'm going to use is 306. So I'm going to say, in fact, 1 is 306 over 306. I'm going to have to multiply 1/6 by 51 over 51. So that's going to be 51 over 306. And then I'm going to have to multiply 51 by 6. So this is going to be 6 over 6 times that. So that's 66 over 306. So 66 plus 51, well, that's 110 for 60 and 50. So that's 117. That's 417 plus 6 is 423. So I'm going to say 423 over 306 is really what that is. Therefore, C equivalent is the reciprocal of that. That would be 306 over 423. Okay. Now that's something that I really am completely cool with using the calculator on. I'm going to first check my work. I do see that 51 times 6 is 306. So I'm good with that. So now I'm going to say 306 plus, obviously I have to multiply 1/6 by 51. So I'm going to add 51 to that to make sure I got the right answer. And then I have to multiply the 51 by 6. So I'm going to have to add 66 to that just to make sure I get the 423. Yes. Okay. So I agree with that. So I'm going to do 306 divided by 423. That gives me 0.723. And of course, I want to keep at least one extra sig fig. So I'm going to say, whoa, no, I'm evidently just going to randomly erase crap because that's what Steve Jobs wanted me to do. So I'm going to say this is 4-0. Both of those are not significant digits because I've, using well beyond the significant digit rules. So that's my equivalent resistance. And that is, in fact, a answer. So I'll circle this like that. So I've gotten part of it. Yay, Mr. Younger. Anybody have any questions about how that was done? Now, believe it or not, that was actually the easy part. Okay. So according to the battery thinks the capacitance is just one capacitor whose capacitance is 700 and, or, well, yeah, we could say 723 nanofarads if we wanted. But that's not really what's there, but it doesn't matter mathematically, equivalently, electronically, that is what's there. So I can now say that C equivalent, I can say C equivalent is equal to Q over V. And this will give me Q is equal to, obviously, C equivalent times V. So that'd be 0.72340. Here's me using the extra sig figs to be certain I don't round too early and too often. And I'm going to multiply that by 12.0 volts. And when I do that, I'll say times 12. That gives me 8.6809. That's 2 extra sig figs there. Notice the micro. This is what I was telling you earlier. This is a common thing we do in a lot of different parts of physics in general. but it really shows itself when you're dealing with electronics. A micro is just a times 10 to the negative 6. So you don't actually have to let that play. You can just do the multiplications and keep the micro there. So I'm just going to go ahead and say, all right, well, the farad part times the volt part gave me a coulomb. So this is 8.6809 microcoulombs. And I should remind everybody that technically right here is a farad. Okay. And in fact, let me up the ante a little bit. I shouldn't have written that as just micro because that's sort of meaningless. But this should be, in fact, micro farads. And then I'll finish my boxing like that. Okay, so now I've got Q as well. And I'm going to box that off so we'll know what that is. That's a really ugly Q. I'm not impressed with that. Oh, that's moderately better. You know, I look like I might eat goldfish in the off time. But anyway, goldfish the snack, you know, like I'm a toddler. Okay. Anyway, so there's the charge Q. We now know what that is. So we've got a couple things done. Now I've got to go through and do the rest of the stuff. So remember what I told you. As far as the battery is concerned, there's just one capacitor over there, and that capacitor has a capacitance of 0.72340 microfarads. So it's going to send out a charge of 8.6809 microcoulombs. It's going to just start trickling it out little by little by little until that much current gets out, and then it's going to be compelled to stop. Okay, because it don't have the electromotive force to push anymore. So what we know is, like I said, that first 1 microfarad capacitor is going to get all of the charge. So I know that, for instance, Q1 is equal to C1. C equals Q over V is what I'm using here. So Q1 is equal to C1 times V. Oh, excuse me. I don't want to do that. I just know C1 is just going to be or Q1 is just going to be equal to the total amount of current that comes out. I also know Q6 is going to be that same amount of charge that comes out. I said current a second ago, but I meant charge. So this is going to be 8.6809 microcoulombs. So I now know Q1 as well. As I said, I'm telling you Q6 is also that, but I'll prove that later as well. So I'm going to write it here for now just so we'll have it. Okay, so now I have some of the values. Now I need V1. This is where I'm going to use C equals Q over V. So V1 from C equals Q over V, V1 is equal to Q1 over C1, which Q1 is 8.6809 microcoulombs divided by 1.00 microfarads. A coulomb divided by a farad is a volt, and a micro divided by a micro cancels each other out. So I can immediately say that V1 is 8.6809 volts. Oops. So that's another thing we figured out. Now I'm going to make use of these bubble things. Remember, the voltage drop going from the positive plate to the negative plate of the capacitor is 8.6809. I know the voltage at the left plate is 12. I already did that with my bubble. So the voltage at the top plate is going to be 12 minus 8.6809. So I can now say this bubble is going to be 3.3191 volts. So that's the bubble there. But notice there's nothing but wire separating this particular spot from this spot and this spot. So those two have the same voltage. Okay, so that's something that can help me as well. When I start to calculate voltages, I can calculate V2, for instance, and I know if I subtract that V2 from 3.3191, I'll have the voltage on the right-hand side of the 2 microfarad capacitor. So that's going to come in handy as well. All right, now here's the deal. We now have that 8.6809 coulombs is going to go to this junction that breaks off to the top part going to the 2 microfarad capacitor and the bottom part going to the 3 microfarad capacitor. But that's a little bit of a problem because I don't know how much is going to the top and how much is going to the bottom. But what I do know is that that top has an equivalent capacitance of C equivalent 2. So I'm going to remind myself of that. And I know, for instance, I'm going to draw right here that I got a wire, and this is Q coming in, and it's breaking off to a capacitance that happens to be C equivalent 2, which is 1.6363 microfarads. And it's also going to break down to this guy down here, which is just 3.00 microfarads. Okay, so actually, let me make that a little bigger so we can see that that's a decimal. Okay, so these wires will come back together like this. And that's what we got. So there's going to be some part up here, a QT for top, say, and a QB for bottom. Okay. So we don't know what that is, but what we do know is conservation of charge applies. So from this, I can get, here's a key point. So make sure you pay attention to the words I'm saying here. Q, the 8.6809, is going to be broken up into QT and QB. So that's the 8.6809 microcoulombs. But here's the other thing. We know that the voltage, because they're in parallel, the voltage of C equivalent 2 and the voltage of 3 has to be equal. So I'm going to say, remember, C equals Q over V. So V is equal to Q over C. I'm going to say Q top over V equivalent 2 is equal to Q bottom over C3, okay, which is just that 3 microfarad capacitance. So that's going to give me Q top over V equivalent 2 is equal to Q bottom over 3.00 micro. Excuse me. Oh, duh. I wrote the wrong thing. On the left-hand side, let's fix this real quick. On the left-hand side, remember I said C equals Q over V. So V is equal to Q over C. So I ended up writing the VEQ instead of the CEQ. Let me fix this real quick. Okay. So again, what I'm using is, maybe I should write this somewhere. I'm going to write this right here. C equals Q over V, which implies that V is equal to Q over C. And it also implies that Q is equal to CV. So those are the three forms that I'm using. Hopefully that'll allow you to refer back to them really quickly and see why I'm using what I'm using in each case. Okay. So what I need is QT over the C equivalent to. So QT over C equivalent to is equal to QB over C3. Remember, C3 is just a 3 microfarad capacitor. So this becomes QT. I'll call this equation 1, by the way, and I'll call this equation 2. This becomes QT over 1.636. I'm getting in that small corner, so everything I do looks like crap. So I'll say QT over 1.63. Damn. Micro is equal to QB for the bottom over 3.00 micro. Now, here's something that I realized earlier today when I was playing around with it, but I didn't realize when I was working with my students on this same example in my face-to-face class. The microfarad, remember, on the 1.6363 is literally 1.6363 times micro times farad, and the 3.00 is literally 3.00 times micro times farad. So I can actually cancel out these, and I don't have to deal with the micro or the farad part. That's going to come in super handy. Okay. So now what I'm going to do is I'm going to call this equation 1 and equation 2, as I've shown here. I'm going to copy this thing that I have. And I'm going to copy it to the next page. I'm going to say copy. Now I'm going to go over to the next page. I'm going to shrink this down, hopefully. And I'm going to say paste. Whoa, Nelly. And evidently I'm going to scroll it and something that I didn't mean to do. Okay. I wonder if I can fit it over here. Yeah, that's good enough. Y'all can see that, right? Okay, and now I'm going to go ahead and draw another black line over here just to separate this out from the work. Okay, so now what I'm going to do is I'm going to take equation 1, and I'm going to say that, in fact, QT is equal to 8.6809 micro minus QB. And I'm going to call this 1 prime, and I'm going to plug 1 prime into 2. So that's going to give me 8.6809 micro minus QB. All that is going to be over 1.6363. Notice I got rid of the micro and the nano So, or the micro and the farad. So that's just 1.6363. And that's equal to the right-hand side, which is just QB over 3.00. So I think everybody knows how to solve this type of equation, yes? Anybody want to offer a way that I'm going to go about solving this? So thank you for your congratulations. I'm going to cross multiply. That's what I'm going to do. Okay, so I'm going to multiply 3.00 times that top left term. So it's a binomial. Remember, fraction bars are equivalent to parentheses, so you have to treat it just like you've got to distribute it over parentheses. So when I multiply the 3 by the 8.6809, I get 26.043. So 26.043. That's my 2 extra sig figs. And that has a micro, meaning microcoulombs, by the way. And then minus 3.00, just a pure number now, times QB. And that's equal to, now I've got to take this 1.6363 and I got to multiply that. That's just a pure number because I canceled out the micro and the farad and multiply it by the QB. So now I can see that the QB has a common term on both sides of the equation. I'm going to pull that over and I'm going to say 26.043, where the 4 and the 3 are superfluous, is equal to the 3 comes over here and this becomes 4.6363 QB. So I can now say that QB, which is really, notice QB is actually Q3. I called it bottom just so y'all understand what I was doing, but that's the charge that's going to hit the 3 microfarad capacitor, period. No ifs, ands, or buts about it. So it's going to be 26.043. I'm going to divide that by 4.6363. And that gives me 5.6. Notice it has a micro up top, so I got to keep that. So it's 5.61. And then the next two sig fig, or the next two digits, which are not sig figs, are 71. 6171 microcoulombs. So I now have Q3. Now, remember, Q top is what's going to go to the top, but what's going to the top, all of it will appear on the 2 microfarad capacitor. So that's the same thing as Q2. So now I'm going to say Q top, Q top, which is really Q2 as well, is equal to, according to 1 prime, that's 8.6809 micro minus QB, which is 5.6171 micro. And that's going to be positive 3.0638. Microcoulombs. So now I have Q3 and Q2. I might as well go ahead and calculate V2 and V3. So is everybody following so far? This is a long, detailed problem, but hopefully you might need to look back, like I said, at the easier examples in chapter 24 first. Just the simple, combining 2 resistors in series, or 2 capacitors in series and 2 capacitors in parallel, and then a slightly harder one, and then look at how the book reconfigures to find the voltage and the charge and all that stuff, and then come back and visit this. It might be a little more helpful if you haven't already studied that. If you've already studied that, this should be somewhat clear, even though it's a long problem. All right, so V3, again, we're using these expressions right here for the various forms of capacitance. So I want to know voltage, that's the charge divided by the capacitance. So I'm going to say V2 is equal to Q2 over C2. Well, that's pretty straightforward. Q2 is 3.0638 microcoulombs divided by 2 was 2.00 microfarads. And as I said, micro and micro cancel out, but a coulomb divided by a farad is in fact a volt. So I'm going to do 3.0638 divided by 2, and that's going to give me 1.5318 or 19. And that's just plain volts. So now I have V2. And V3, whoops. V3 is equal to Q3 over C3. We already know that Q3 is the 5.6171. So I'm going to take the 5.6171 and divide it by 3. And again, the same unit stuff worked out there. So 5.6171 divided by 3 gives me 1.8724. And that's volts. So I now know V3 as well. And I could put the underline on the 2,4 there. Okay, when we last looked, I had computed that 3.3191 was the voltage at the top of the 1 microfarad, but also at the left of the 2 microfarad and at the left of the 3 microfarad. So let's copy that over here. 3.3191 volts is our bubble. And that corresponds to this point, and it corresponds to this point, and it corresponds to this point. So now if I know 3.3191, and I know that the voltage drop across 2 is 1.5319, then minus, I'm doing 3.3191 minus 1.53. So let's do this. This is going to be 3.3191 volts minus 1.5319 volts is equal to 1.5319 is equal to 1.7872 volts. So what that tells me is that this voltage right here is 1.78. And I'll go ahead and write 7872. So that's the voltage there. Now I can also do the same thing. I can do 3.3191 volts minus Now I need the voltage across, crap, did I use the wrong voltage? The voltage across 2 was 3.5. Crap, I did use the wrong voltage. Let's do boom, 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 boom. Notice, everybody, I took V3, not V. Well, actually, I did take V2, didn't I? Oh, crap. Yeah, I did use V2. 3.3191 minus 1.5319. Yeah, that looks good. Okay, I can put that all back. Boink, 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 boink. Okay, so I now know that voltage there, and I can also do the same thing across V3. I just need to use the voltage across V3. Yeah, that I was looking at 3.0638. That's what was throwing me off and thinking I'd used the wrong voltage. So in this case, I'm going to do 3.3191 volts minus 1.8724 volts. And that's going to give me the voltage drop across the 3 ohm resistor. So I'm going to do, or excuse me, a 3 microfarad capacitor, 3.3191 minus 1.8724. And that gives me 1.4467. So that's just the voltage on the other side of the three microfarad capacitor, which I can put right here. And I'm going to say that voltage is 1.4467 volts. I'm going to put it in a bubble. And I'm going to tie it right here. But I think you all notice that that also has to happen to be the same as the voltage right here, which is the same as the voltage right here. Okay. So that helps me a little bit because I know that this voltage, the 1.7872, also has to correspond to that voltage, and it also has to correspond to that voltage. But this 1.4467 also has to correspond to this voltage. So that last one I drew was kind of stupid. I'll draw it this way. And to this voltage. So all those voltages are the same. I think you can now see that the voltage drop across the 4 ohm, 4 microfarad capacitor is going to be basically 1.7872 minus 1.4467. And that can actually be used to get the charge Q4 and the charge Q5 as well, because that's going to be the same drop across there. All that's possible. Now, what we do know is that the charge on Q2, which I wrote up here, is 3.0638 microcoulombs. That's how much charge is coming from the 2 microfarad capacitor, and it's going to be split to make the part that goes to the 4 microfarad and the part that goes to the 5 microfarad. So I could also work it that way. I can say that the Q2, oops, let's say the Q2 has got to equal the Q4 plus the Q5. And of course, the Q2 we already know is 3.0638 microcoulombs. So let's call this equation 3. But we also know that 4 and 5 are in parallel. since 4 and 5 are in parallel, we also know V4 is equal to V5. And of course, looking at voltage, voltage is Q over C according to that little area right there. Okay. So I can say Q4 over C4. So I'll say Q4 over 4.00 micro is equal to Q5 over 5.00 micro. Again, that microfarad and microfarad can cancel out, and I can call this equation 4 right here. So now I can use equation, let's use equation 4. So from equation 4, I get that Q4 is equal to 4/5 Q5. That's helpful too. That's something you need to understand is obviously the lion's share of the charge goes to the item with the largest capacitance. So the 5 microfarad capacitor gets a bigger chunk of charge than the 4 microfarad capacitor. So I've got that, and I'm going to call this 4 prime. And now I'm going to plug 4 prime into 3. And that's going to give me, that's going to give me 3.0638 microcoulombs is equal to Q4, which I'm going to say is 4/5 Q5 plus Q5. So basically all I did was replace Q4 with 4/5 Q5. So 4/5 plus 5/5 Q5 gives me 9/5. So I've got 3.0638 microcoulombs is equal to 9/5 Q5. So now I can say that Q5 is equal to 3.0638 times 5 and then divided by 9. And that's 1.7021 microcoulombs. So I now have Q5 as well. And I can now also figure out Q4 by multiplying that number by 4/5, which is, of course, 0.8. That gives me 1.3617 microcoulombs. I can square that off. That. Okay. Now, for internal consistency, we can check whether I was right. I suggested, let's do it this way. I suggested V4 equals 1.7872 volts minus 1.4467 volts. Notice the last 2 of those digits are not significant, so we don't expect them to be that right out to 3 and 4 decimal places, but we do expect them to be right to 2 decimal places. So I'm going to say 1.7872 minus 1.4467 is equal to 0.3405 volts, and V5 was also supposed to be 0.3405 volts. But V4 is actually supposed to be Q over C. So if I take my Q for 4, that's Q4, I'll say but Q4 over C4, which is equal to 1.3617. Hopefully this works out right, because otherwise I've made some kind of careless mistake. These are the facts. It has to be this way. So if I take this 1.3617 and I divide it by 4, I better get the same voltage. And that does give me 0.34, check this out, 3404. So it's still pretty close, even to decimal places that aren't consistent with the sig fig rules. Okay. V5, on the other hand, should be the same thing, the 3404. So V5 is equal to Q5. Actually, Q5 over C5. So I'm going to take the Q5, which is 1.7021, and I'm going to divide that by 5. Plus 5 microfarads is the capacitance. Whoa, Nelly. Oh, no wonder. And that gives me 0.3404 volts as well. So we now have Q4, Q5, V4, and V5. So I can go back and click on, oh, and I also had V3 already, didn't I? Where was V3? Yep, I did that. So I also had V3, Q4, V4, Q5, V5. Okay. So now we've gotten everything but Q6 and C6. And what I told you Q6 was going to be was exactly the same as Q1. Specifically, Q6 was going to be 8.6809 microcoulombs. Of course, the 09 is not within the sig fig, so we don't expect that part to be right. But that's what it's supposed to be. So I'm going to say again, I also suggested that Q6 equals Q1, which equals 8.6809 microcoulombs. And now we can see if that is consistent with the voltages. Okay. So if I look at this, this suggests to me that the voltage there at the top plate of the 6 microfarad capacitor is 1.4467. And of course, this being 0 volts right here means that it's also 0 volts right there. So that means the total voltage across capacitor 6 is 1.4467. So let's check that. I'll say for the voltages to be correct. The V6 must be 1.44. What did I say that was? 67, 1.44. Yeah, 67 volts. But using my suggested Q6 equals 8.6809 microcoulombs. The voltage turns out to be V6 is equal to Q6 over C6, which is equal to 8.6809 microcoulombs divided by 6.00 microfarads. So 8 divided by 6 gives me 1.4468 volts. So that's also pretty close, even in the fourth decimal place. We predicted it should be 1.4467, but we got 1.4468. This allows us to be greatly confident that the calculations were correct. I should say are correct. I don't even like this whole thing here. Okay. So any questions on that? So we now know Q6 is equal to 8.6809 microcoulombs and V6 is equal to 1.4467 volts. Any questions on that? All right. Well, that's taken me about an hour and a half. So let's go ahead and take a break. And that's okay. I don't mind spending an hour and a half. I mind the fact that probably a lot of you get lost when I go that long, but I don't mind spending the whole hour and a half explaining that. What you need to do, probably, unless you followed everything, what you need to do is go in, play the YouTube video when I post it on my YouTube channel, play for 10-15 minutes, however long you can pay attention, and pause it frequently, making sure you understand everything I say, and then making sure you can verify everything I calculate, and then start up again. And if you feel like you're getting overwhelmed, then just take a break for a little while and then pick back up where you left off. Okay, so that's basically it. But that's sort of the mother of all nasty butt problems. So hopefully that will help you guys in doing even the nastiest of problems. And this is This is not, believe it or not, not really an unreasonable problem to put even on a test. I probably would not put it like on a midterm or a final, because midterms and finals generally include several chapters. So it's really hard to force someone to go really deep on one particular chapter. So I still consider it to be fair game for a midterm or final. I just probably wouldn't put it on there. Okay. But it is certainly reasonable for a test. So make sure you guys can do things like this. You'll see that your book does a problem somewhat like it. I'm going to go ahead. It's 7 o'clock right now. I'm going to tell you guys to take a 10-minute break, come back at 7:10, and then I'll show you another example, but I'll also show you the example they did. So go ahead and take that. But I'm here if anybody has any questions, so feel free to ask me. About 4 minutes left. Feel free to ask me questions. Like I said, you guys are open to it. I'm open to taking them. I've got about 2 minutes left. I'm gonna go ahead and put up a screen I want to share with you guys so you can see an example that is obviously much easier than the one I just did. But it's actually, I worked it as if mine was just one big example. They worked it as if theirs were two smaller examples. So it's a little bit comparing apples to oranges, but still somewhat relevant. We'll talk about that when time is up. All right, it's time to go ahead and start cranking. I just thought I'd write a couple golden rules. I'm going to show you those in a second. So first off, and actually you can make four of those golden rules for the record. But what I wanted to show you was what your book did was example 24.5 and 24.6. 24.5 is sort of like the first half of the problem I just worked for you guys, where I first computed the equivalent resistance. Notice how much easier this circuit is than the circuit we did. Okay. That's the key. Okay. And not only that, notice the rules. What we do is we try to find two components. In this case, they were capacitors, but two components in capacitors that we could actually use one of our formulas for to compute the equivalent capacitance. Well, in this case, we can't do it with C2 and C1 because C2 is not really in series with C1. Neither is C3 in series with C1, but C2 and C3 are in parallel with each other, so we could use the parallel formula. Then once we have that, then we have the equivalent resistance of C2 and C3 is in series with C1, so then we can use the formula for that one. So that's all they're doing there. And you see it comes out really nice. In fact, that since they called them all C, they all had a capacitance C, the net result is 2/3 of C. One thing you might notice with capacitors, when they're actually in series, the net capacitance of a series is smaller than any one of the capacitances in the series. And when they're in parallel, the net capacitance is bigger than every one of the capacitors in parallel. We'll find that exactly the opposite is true when we deal with resistors. Now that you have those equivalent those equivalent capacitances, in example 24.6, they're going to ask you to find things like Q2 and Q3 and Q1. In other words, the charges on those in V3 and V2 and V1. And that's what they do here. So there's their V1, V2, V3. There's Q. Q they get from the equivalent capacitance, which you can see was 2/3 C. Q1 they can work out. Q2 they can work out. Q3 they can work out, so on and so forth. But this is just a simpler, much easier problem to do. And if you've done that, that might seem, the problem I just did might seem a little easier. If you hadn't looked over that and thoroughly understand it, then yeah, the thing I just did was really, really tough probably. So I understand if you don't get that, but anyways, definitely look back over it and then try looking at the video of the ones we just worked. I'm going to actually now stop sharing that, and I have sort of another circuit. This was going to be exactly the same difficulty as the one in the book, but I have another circuit that I'm going to work, and this one's with just capacitors, but it does a weird thing. But again, it helps you understand how capacitances behave in circuits. So let's start off by sharing my screen. So I'm going to share my iPad screen. And it acted pretty quick last time, at least initially, but then it took forever still. So it'll come up in a second. Put the chat back up. I got that up, and I got your faces up as well. So I put these two golden rules here because those two came in handy. What I wanted you to realize is two parallel legs of a circuit. And I had to say legs of a circuit because, like, if you look at that leg that has the 4 microfarad capacitor, that is one leg. And then the leg with the 5 microfarad capacitor has one leg as well. But if you look at the whole leg, that includes the 2 microfarad capacitor in series with the 2, 4, and 5 microfarad capacitors that are in parallel, then that's a whole leg by itself. So I had to allow for all those possibilities. So I just said two parallel legs of a circuit always have equal voltages. So what I mean is the voltage difference from, let's mark this with a distinct color. The voltage difference from here to here by going this way is the same as the voltage difference by going down through the 3 microfarad capacitor and then back up. And that's what number 1 says, is the total voltage across all that junk on the top is the same as the total voltage across all that thing, that one thing on the bottom. Now you could also add to that the sum of the currents, or the sum of the charges going into that top leg, and the sum of the voltages or currents or charges going into the bottom leg have to add to give you the total charges or current coming into that split right here. So that would be like rule a golden rule number 1B or something like that. You could do it that way, or you could just call it rule 2. So that's another thing that's in there. But for this particular example, I wanted to just point out that this was very much what I used, was this rule 1 and rule 2. Now, rule 2, it says 2 items in series have a net voltage change equal to the sum of the 2 changes. That means that if I take the voltage from across the 2 microfarad capacitor and add that to the voltage across the 4 microfarad capacitor, then that'll be the total voltage across the green dot to the green dot. Okay, so again, that's something else I use. Not only that, you could add to it another rule. You could say the total current going into say, or the total charge, either one, going into the 2 microfarad capacitor is equal to the total current going into the 4 microfarad capacitor plus the 5 microfarad capacitor. So that's another way of looking at it, and that could be like 2B, or it could just be number 4, and number 2 would be number 3. But those are just some of the circuit rules you already learned in lab, hopefully. But I just wanted to reiterate them here because they're what we used to work out that previous problem. So now that I've got that done, I'm going to show you a neat little problem. So what I'm going to do is I am going to take a battery, and let's say this battery has a voltage of V equals 100.0 volts, and I am going to put it in series with a parallel bank of capacitors. So this first capacitor is going to have a 2.00 microfarad capacitance. Oh man, that just stinks. Okay, and then that 2 microfarad capacitance is in parallel with a 4 microfarad capacitor. I like to deal with these capacitances that are exact multiples of one another, so you can see exactly how that what the ramifications of one capacitance being twice as large as the other, because a factor of 2 difference in a number is usually easy to change, easy to recognize. Like 36 and 16 you don't recognize, but 36 and 18 you do, or 32 and 16 you do. Okay, so that's what's going to happen here. So what's going to happen is I'm going to connect these 2 parallel capacitors to the battery. The battery, of course, is going to send out a charge Q that's basically based on what the equivalent capacitance of the 2 capacitors are. And that charge, part of it will go to the 4 microfarad capacitor, and a smaller part, in fact, I suspect about half as much, will go to the 2 microfarad capacitor. And in fact, that's going to establish a charge Q4 up here and a charge Q2 up down here. Those are some charges I'm going to want to know. So those are, I put question marks by them because that's part of the problem that you're going to answer. Now, the next step I'm going to take is I am going to disconnect them. And I'm going to have basically just a wire sitting here, and then the 2.00 microfarad capacitor is just sitting there, and the 4.00 microfarad capacitor sitting there. But now it has obviously a charge of plus Q4 4 here, and minus Q4 there, and plus Q2 here, and minus Q2 here. But I'm going to boom, disconnect them. And now I'm going to take this chart or this top part and I'm going to leave it be. And it's going to have a charge of plus Q4 here still. And this is the 4.00 microcoulombs. This is going to have the minus Q4 here. And then I'm going to connect it to this one, which is the 2.00 microfarad capacitor. But in this case, I'm going to have the minus Q2 here and the plus Q2 here. In other words, I flip them around. And the ultimate result will be basically that I have this capacitor and this capacitor with new charges. This one's going to be Q4, and this one's going to be Q2. And of course, this is still the 2.00 microfarad capacitor, and this is still the 4.00 microfarad capacitor. So I want to know what is Q4, Q2, Q4, Q2, and let's call this V prime, where V prime would be the voltage difference. Let's draw a little multimeter here. V prime. And let's draw a little black wire that goes from here to here. And let's draw a little red wire that goes from here, excuse me, to here. Okay. So that's really what I'm trying to figure out is those quantities. Your book does a problem just like this, except they use different numbers. I don't think that's quite as instructive, and I'm trying to use these as if they're getting multiple things at once. So first off, what we know is that in the initial setup, we have a 100-volt battery, and that's put essentially in parallel with a 2 microfarad capacitor and a 4 microfarad capacitor. And that tells us that, here's our solution. So the things we're going to use for our solution are C is equal to Q over V, which also gives V is equal to Q over C, which also gives Q is equal to CV. Okay. What I do know is that V is equal to 100.0 volts, which also equals V4 and also equals V2. In other words, that is the voltage across capacitance 2 and capacitance 4. And notice it doesn't have the prime on it. That's why I know it's different than the last voltage that we're looking for. So all I have to do to actually calculate the capacitance, or excuse me, the charge Q2 and Q4 is as follows. So Q2 is going to equal C2 times V2, which of course is 2.00 microfarads times, in this case, V2 is 100.0 volts. So this is going to give us 200 microcoulombs. Because 2 times 100 is obviously 200. Similarly, Q4 is going to equal C4V4, which is going to be 4.00 microfarads times 100.0 volts. That's going to give me 400 microcoulombs. Again, I'm just using the principle that basically the micro is just a multiplier, so I don't really have to convert back and forth between the base unit and the prefix unit, I can just leave it on there, and the micro will apply equally well to the coulombs as it did to the farads, as it does to the volts or whatever. So I've got part of that. Does everybody see how I did that? Any questions on that part? All right. So the next part, I was just laughing at Elron. So anyways, so the next part, we're going to actually disconnect these. Now, let's try to see what's really going to happen here. So what I'm going to do, according to this third drawing, so notice I'm counting from left to right. The first one's the first drawing, the second one's second drawing. The third one is the third drawing. And you'll notice that I'm going to take Q4, which we just decided was 400 microcoulombs. So what happens when I connect positive 400.0 microcoulombs to negative 200.0 microcoulombs? Anybody tell me what can happen there? How about you, Nora? You skipped last time. You ain't said a darn thing the whole class today. Trying to ignore me. Actually, I think she's got me muted. So anybody know? So I'm literally going to take positive 400 microcoulombs and touch them to negative 200 microcoulombs. What's going to be left?
Professor?
Yes.
It takes a while to heal. So
Yes. Nora, did you say something?
Oh, okay, I didn't know if you were addressing someone else.
No, I was picking on you a second ago.
Oh, okay.
Yeah. I said you ditched last time and you ain't said anything today.
Ditch. You can't say ditch, Professor.
I have no idea what you did. I was just being funny.
That paints me in a bad light, okay?
So what happens when I take 400 positive microcoulombs and on a wire and touch it to a negative 200 microcoulomb wire? What's going to happen with the positives and the negatives?
Man, they're gonna cancel out, so you just have 200 left.
Exactly. They cancel out, leaving positive 200.0 microcoulombs. That's an important point because that's what happens between the third picture and the fourth picture. And in fact, that's all we've got to work with Q4 and Q2. So in fact, what we can conclude is that Q4 minus Q2 is equal to Q4 plus Q2. That's mathematically how I write exactly what Nora said, and exactly what probably all y'all are thinking. It's just I said the question in such a generic way, it might have been not been obvious what I was asking. So from this, I now have that 200.0 microcoulombs is equal to Q2 plus Q4, which the OCD in me just won't let me continue to write the Q4 before the Q2. Okay. Now, the other thing is these two guys are in fact in parallel. And if you're not so sure about that, I get it. Trust me. Just notice that the whole left-hand side is one conductor, and there's no way for that to have a different voltage at one end than it has at the other. So that whole left side has a specific voltage, and then that whole right side has another specific voltage. One of those is high and one of those is low, so there's nothing you can do about it. All right. So yes, they are in parallel. Since they're in parallel, what we know is that, let's see, C2, or excuse me, I'll write it this way. Oop, I don't know why I went there. That's weird. I just noticed some little dot things happening on the screen and I don't know why. All right, so I've got my blue marker. I'm going to say the 2.00 microfarad capacitor and the 4.00 microfarad capacitor. Remember, another word for that is condenser, so you can sometimes say that, are in parallel. So V prime is equal to V2, which equals V4. That means from our V equals Q over C, that means that Q2 over 2.00 microfarads is equal to Q4 over 4.00 microfarads. Here's another wonderful example where you can just cancel out the micro and the farad. And what we see is, in fact, that Q4 would equal 4 over 2 Q2, which is just 2 Q2. Okay, so I will call this equation 1, and I'm going to call this equation 2, and I'm now going to plug 2 into 1. And when I do that, I am going to get 200.0 microcoulombs is equal to Q4 is 2Q2. So I'm going to leave Q2 to be Q2 and then say plus 2Q2. So this is actually equal to 3Q2, which implies that Q2 is actually equal to 200 divided by 3, which I think you all know is like 666 or 66 point something another. But anyways, 200 divided by 3 is equal to 66.66. So I'm going to say 66.66 microcoulombs is Q2. And then then Q4 is equal to 2Q2, which is equal to 133.3 microcoulombs. So now I have Q2 and Q4 with the lowercase case. And now I can also find that V prime is equal to Q2 over 2.00 microfarads. I could use the other one. It doesn't really matter which one, but I'm going to use this one. The Q2 is 66.66 microcoulombs divided by 2.00 microfarads. The micros cancel out, and I just get 33.33 volts. And I don't know why I did all that in red this time. I normally try to catch myself, but I'm still going to use a different color to box the answer. And that's the final answer. So notice in doing all that process, we lost some of the charge by reconnecting them backwards. And that resulted in a net decrease in the amount of voltage, because before, when we used the battery, the voltage was 100 volts because that's what the voltage of the battery was. But by disconnecting it, that meant charge wasn't necessarily free to move, but because we reconnected them, the positives and negatives could cancel out, which could mean the total charge could decrease. But then the voltage had to lock down and stay the same. In this case, the final voltage was 33.33 volts. So any questions on that? And notice also how, as I said, since C equals Q over V, you see C and Q thumbs up, that means they're directly related. That tells you that when you have a certain amount of charge coming into a parallel bank of capacitors, the capacitor with the largest capacitance is going to get the lion's share of the actual charge. And in fact, the ratios of the capacitance tells you exactly how much that was, as you saw that the ratio was 4:2, and therefore the 4 one got twice as much as the 2 one. Okay, any questions on that? All right, I'm going to stop sharing this one right quick, and I want to go and show you a couple more conceptual problems. We just did a pretty tough conceptually tough problem, but it wasn't that really hard mathematically. It certainly wasn't as difficult as the previous problem. But what I'm going to do is I'm going to now share the screen using my book. And I'm going to do share screen, book screen. There I am. Okay, so this is the derivation of the formula U equals 1/2 Q squared over C. There's different ways you could derive it. The main thing is I always remember this form right here, 1/2 CV squared. The reason being is it looks just like 1/2 MV squared. It looks just like 1/2 KX squared, so on and so forth. And that's a famous thing. So for instance, if you talk about a mass on a spring, what you know is going on with a mass on a spring is the spring has a kinetic energy given by 1/2 KX squared. And then the mass on the spring has I said kinetic energy, didn't I? The spring allows the mass to have a potential energy of 1/2 KX squared, where X is the amount of compression or stretch beyond or within the equilibrium point of the spring. So the potential energy is 1/2 KX squared. On the other hand, the other form of energy is kinetic energy. So we're imagining, for instance, a rock a mass on a spring, and the spring is mounted to a wall over an ice skating ring, so it has essentially zero friction, and that mass can oscillate back and forth. And what's going on is the energy is oscillating back and forth to a maximum stretch, where all of the energy is in the form of potential energy, 1/2 K, not X in this case, but A squared, because A is the amplitude of the oscillation. And then it's going to go from X equals A all the way to X equals 0. At that point, you're at equilibrium, and there's no force acting on the spring anymore to try to speed it up or slow it down. So when you go to do that, it's basically maxed out its velocity, and now the total energy is 1/2 mv max squared. And then it's going to continue with that velocity and slow down as the force from the spring increases until it gets to A again, the amplitude, only this time it's the amplitude in compression instead of in stretching. And now the energy is all potential energy again, 1/2 Ka squared, and back and forth. So when you have two systems like that, where the energies are sloshing back and forth, you know what's going to happen. You're going to go from one extreme to the other. In this case, I've got a kinetic or a potential energy of 1/2 CV squared. And I'll tell you that another circuit element is going to have an energy 1/2 Li squared, where I is the current going through the circuit. And in fact, when you have an AC current going through a circuit that has a capacitor and an inductor, then yes, the energy is going to slosh back and forth just like it did in the harmonic oscillator problem, only it's sloshing back and forth from U equals 1/2 CV squared, where V is the voltage, and 1/2 Li squared, where I is the current. And in those cases, when it's all in forms of the energy of the capacitor, then it's 1/2 C V max squared. And when it's all potential energy of the inductor, it's going to be 1/2 Li max squared. Okay, so that's kind of relevant. And it also gives us the formulas that we can use stored in the capacitor. And there's a nice, simple little problem. Hey, here's one. A camera flash unit stores energy in a 600 microfarad capacitor at 330 volts. How much electric energy can be stored? Well, that's something where they gave us C, they gave us V. So that tells us this middle formula, 1/2 CV squared, is perfect because I've got C and V. So that's all you're going to do is calculate that, and your book does it and gives you 36 joules. Then it says, what is the power output if nearly all the energy is released in 1 millisecond as a flash of light? Well, power is energy divided by time. So really all they're asking you to do is take the energy that was released, the 36 joules, and divide that by the time, which is 1 millisecond. So you end up getting 36 kilojoules, or excuse me, in this case, kilowatts or kilojoules, depending on how you want to do it. But as power, it'd be kilowatts. And that's basically because the milli in the bottom becomes a kilo in the top. Now, let's look at example 24.9. This is a concept I want to make sure you guys can understand. So it says a capacitor plate separation is increased. So a parallel plate capacitor carries charge Q and is then disconnected from a battery. Key point here, big concept for this chapter. When you disconnect a capacitor from a battery, the voltage is free to do whatever it wants, but no charge can leave it unless you sort of are breaking open the capacitor and doing crazy stuff. So when they say, hey, we disconnected a battery, that's code word for voltage is going to change, but the charge has to stay the same, period. Okay. Similarly, if they say we left the battery connected, that means voltage is going to be locked down and can't change, but the charge can change ad nauseum. Okay, so keep those concepts in mind. And also keep in mind that capacitance is Q over V, and capacitance for a parallel plate capacitor is epsilon 0 A over D. Unless you have a dielectric, then it's K epsilon 0 A over D. So right here, it says a parallel plate capacitor carries charge Q and is then disconnected from a battery. The two plates are initially separated by a distance D. Suppose the plates are pulled apart until the separation is 2D. How has the energy in this capacitor changed? So energy for a capacitor, as I told you, the formula I remember is 1/2 CV squared. Well, for a capacitor, the capacitance, a parallel plate capacitor, the capacitance is epsilon 0 A over D. We're not tweaking the A at all, so we have to leave that. But what we went from was epsilon 0 A over D was the capacitance to epsilon 0 A over 2D was the capacitance. So the capacitance actually went down by a factor of 2. So in U equals 1/2 CV squared, U went down by a factor of 2. V can change. So that's a bit of a problem because we don't know exactly what the new voltage is. So that's not a good formula for us to use. In fact, we want to use things whose quantities we know. So if I go back up here, I can say, wait a second, I know exactly what the capacitance did. And since I disconnected the battery, I know that the charge couldn't go anywhere. So I also know that the Q will remain the same. So I'm going to use 1/2 Q squared over C. All right, with that in mind, the energy is now Q squared over 2C. So I've already computed that the capacitance went down by a factor of 2, but now the energy is 1/2 Q squared, which doesn't change. And they told us the energy was Q, or the charge was already Q, but the capacitance went down by a factor of 2, and the capacitance is in the denominator. So that means the energy is actually going up by a factor of 2. So when they ask, how has the energy stored in this capacitor changed? It increased by a factor of 2. So we had a capacitor like this. We charged it up to a charge Q. It had a capacitance of epsilon 0 A, the surface area, divided by D, this little separation between the two. And then I took and pulled it apart. Those two plates, one's positive, one's negative. Are they attracted to each other or repelling each other?
Attracted.
Yes, they're attracted. And the reason why I ask you that is because that tells you if they're attracted, am I going to have to put a force in there to pull those plates apart, or are they just going to try to move apart by themselves?
Gonna need an external force.
Exactly. So the fact that the energy went up by a factor of 2 sounds like we just created energy like a perpetual motion machine, but no, we didn't. We actually put work into the system by pulling it apart to double the distance. That is the work that went into increasing the energy by a factor of 2. Okay, so that's how that works. There's another problem, example 2410, that you can see here, and this one's really fun. I'm going to work this one and a couple of other problems next time on Monday, and that should be plenty of work to finish off chapter 24. So we're going to do that. I just ran out of time. We can't fit any more in. However, I have done the rest of these on my YouTube channel in the past, so you can certainly look at those and get a feel for how 2410 is done and how specifically you can derive this formula, which is what I told you I was going to derive, and how you can solve not that problem, but this problem, inserting a dielectric into an isolated capacitor, dielectric removal, and then this last problem here. All of these, I will be doing something equivalent to it, even though I make up my own problems. I'll be doing something like it. A dielectric partially fills a capacitor next time. But we're done with chapter 24, and we're done with, well, I say we're not done with chapter 24. Once I finish those examples like those, we'll be finished with chapter 24, but we're finished for the day. You guys are free to go. Hopefully you can look at these later, but definitely check out the other videos on capacitors filled with dielectrics, pulling dielectrics out, putting dielectrics in. Those are things that you want to be a little bit well versed on before I go over those examples, so that you can ask more helpful questions as opposed to questions you probably would have figured out on your own. So have a good weekend, everybody. Don't forget to take your test, get your test done by Sunday night. And then there's another one that comes the following Sunday night. And then Wednesday, of course, you're going to have one in class. I'm still leaning towards chapter 24 being on it. So make sure you guys read this chapter 24 and watch these videos. The last bit of covering it will come on Monday. Bye, everyone.
So, Professor, we have a test this upcoming or the week after
Wednesday.
next week.
Yeah, Wednesday of next week, which is the 19th.
Okay, 19th is the online test. That's 22 and 23.
Okay, so 19th is the face-to-face test that you'll have at Mr. Mistral's.
Okay, gotcha.
That's on the Wednesday, the 19th. The 16th, you'll have a online test due on your own, which is a Sunday. And then on the 23rd, I think it is, you'll have a online test due as well.
Okay, gotcha.
Okay.
16th, 23rd online, and then 19th in person. And
Yeah,
we're
and
still hearing back
19 is going to go up through 24.
up.
On
Okay,
19th.
gotcha.
Okay.
Okay. You released the practice test for those already, right?
Yes, they were released a couple days ago, and now
Okay,
the
gotcha.
actual tests are ready. So you can, and one of them, I think I give you 3 chances on both of them, I think.
Gotcha. Okay, sweet. Thank you. And we use the same lockdown browser thing.
No, I'm not even requiring a lockdown browser for these. I changed my mind and just let you have them as open, as fully online tests where you can use open notes, open books, open internet, Google searches, all that good stuff. The 19th one's
Okay,
going to be
gotcha.
a lockdown browser one, though.
Of course. Yeah.
Okay.
Okay, thank you.
You're welcome. Have a good
night.
See you, Nora. Thank you, Zhang. Thank you, Elron. Anybody else have any questions? Looks like everybody's doing okay. I don't know who else is here. Looks like everybody's gone. Stop sharing. I'm the only participant. That's it.